Oh, good evening. How is everybody? Just try to make sure that this thing's working right. Okay. All right, so this evening we're going to talk about three different things. We're going to kind of segue into one another. This one is historic mortars, the chemistry behind what binds our built environment. So it's going to be somewhat technical. Hopefully I'll be able to explain it for you in an easy way. If at any point you have any questions, just raise your hand. I'll try to point you out and let you know if we can get to it, or if it's a really interesting question, I'll try to answer it right away. And of course, there will be questions and answers about 10 minutes after this particular PowerPoint. So we'll get started. Let me jump back. The brief introduction, I'm Randy Ruth of LimeWorks.us. I was asked here today to give a talk about different things, a lot of it being historic restoration based. And when it comes to masonry, you look around Lancaster City, the majority of the buildings are made of brick or stone, brick and stone foundations, wood being an essential component, but it's not the primary element that everybody will see. It doesn't necessarily take the brunt of weathering, and aesthetically, people want to have their brick facade repaired. So, next to just the bricks, an essential component is the mortar. So here, what is mortar? And it's a mixture of various components, including lime or cements, which there is a pretty big difference that we're going to go over, sand and water. And together that kind of adds the glue or the cushion between these masonry elements, whether they be brick, stone, terracotta, and they can also be used as plaster. So plaster and mortar, there's only a little bit of a technical difference with additive, but they're essentially, the root of it is just the same. What mortar is not is concrete or cement. Concrete is something that is well compacted together. You would never use concrete to bind a brick or a stone together. And cement is also not necessarily mortar, because cement's a component of that, and also not all the time. So we have different types of historic mortars, probably the oldest being gypsum. Gypsum is something that's very fast setting. It works in arid climates. It was used for interior plaster and stone mortars in the Great Pyramids of Egypt. That also kind of depends on what studies you look at, and if you look at a study from 2 years ago versus 15 years ago, there's a lot of debate. And I'll be getting into that as well. That even mortars, there's not that great of an understanding, as much as you might think, that we would all be able to understand what actually binds this built environment, because some people will debate that it's this or that, but primarily what you're going to learn is essentially the basics. So the next part would be the lime. The lime, like I said, depending on what study you're looking at, they were used in the construction of the Great Pyramids as a cushion. And it's been a primary building material for 3,000 years, only up until about 1824. Another key component is natural cements. Those are also relatively new, or they were invented around 1818 in the United States. Again, a relatively newer material that's gone the wayside. And then also Portland cement, which is what we all know, a lot of people think of when they think of mortars, would be lime, cement, sand, or quickcrete. That's mostly Portland cement. And that was only invented in 1824 in the United Kingdom, or England. And also in 1870 is when Portland cement first really showed its face in the United States, and that was even as an imported product. So going back to that essential key component, lime, that's been around for 3,000 years, there's three basic types. You have a high calcium limestone, which is mainly composed of about 90 to 100% calcium carbonate, which is the shells and marine life and sediment that's been compressed into a stone under the ocean floor for thousands of years. It's very pure. It's used in all types of chemical processes today, whether it be in the steel manufacturing, water treatment, and also in mortars. The next one is dolomitic limestone. Dolomitic limestone is something that has a little bit of magnesium added to it. It doesn't really work as well, and in fact, you can get dolomitic limestone ready to be used as a masonry mortar from any masonry supply house from around the United States becomes the primary, not binder, but additive to make modern mortars work. Because without it, it won't work that well. Although there's merit behind high calcium lime being used today, which we're going to get into. Then there's also magnesium lime, which has a lot of impurities. It's not really used commonplace. It's used more in agricultural lime or as a filler. And there's also some reasons why you shouldn't even use it as a building stone or an aggregate in the sand that's composed in a mortar. Now, the virtues of lime mortars is that they have hexagonal plate structure. So they actually, these crystals actually go together. They slide together. They're not hard, but they're very flexible. This can be seen in this photo of the lime cycle. So here you have calcium carbonate, or just that limestone. We'll deal with pure limestone. And that would be taken up as rocks or small fist-sized stones, hopefully, and put into what would be a lime kiln. Lime kilns come in all different shapes and sizes. You could go down many historic roads. Maybe you might even be on Lime Kiln Pike or Lime Kiln Road. You find them all over the United States. Over in Wrightsville, there's a whole bunch of them, I believe 7 or 8 of them, right along the Susquehanna River that you can go and visit. It's considered a state landmark because of how important lime was to all industries over the course of the United States and even prior to that. But when you burn the limestone, you get something called quicklime. And during the burning process, that calcium carbonate, the CO2 and water are driven off. So now you have this stone that weighs actually 33% lighter. And it doesn't look like anything else. It looks like the stone that you pretty much put into this kiln. But it's highly reactive. If you were to add water to this stone, it would actually turn that water into a boil. And that stone would start to melt, and it would turn into a putty. And that's where we would get calcium hydroxide, or lime as we know it. Today, you would see it in the form, not in a putty, usually, but in a powdered form, because just enough water was added to turn it into a powder so we could transport it, and we're not spending all this time transporting buckets or 55-gallon drums of calcium hydroxide for building purposes in this very heavy form, or in a very caustic form and dangerous form as calcium and quicklime, calcium oxide. And from there, we would end up adding sand to it. Sometimes they would take this quicklime, add sand and water to it simultaneously, and you would see that that particular method in building for primarily stonework, sometimes brickwork, and you can see that, you can tell that this was done. If you ever look at a mortar, you can see little blips or little nodules of white. Most likely, that's an imperfection in the mortar mixing, and that would be an indication of a pure lime mortar, especially if any building's built before, definitely before 1818 in the United States, probably even in this area, all the way up to the early 20th century. So when you have that, you have this calcium hydroxide, you add sand to it, and you mix it, and you lay a brick with it, you lay a stone. That is mortar. That's the essential basics. And you could even use that to put it on the side of a house, or what many people might see in this region as an old stone farmhouse. Many times those were actually used to, they would build up a stone wall haphazardly, just get it done. Structurally it's sound, but they would actually stucco it on the exterior with this line it out to make it look like cut limestone. Kind of the trompe-l'oeil, or would fool the eye into thinking that this was a very square cut limestone building. But the only way for this particular lime, to get hard and become durable of a material is if it takes that carbon dioxide back from the atmosphere. That's called carbonation. If you have, in some cases, if there's some impurities and it's burned at the right temperature, usually accidentally, you would end up getting a somewhat hydraulic set, which means that it sets with water, it'll end up getting harder, or it'll set faster. but for many years that's just so happened, and the guy down the street named Joe, who was burning limestone for all these different purposes, whether it be for chemical purposes or for building purposes, that was his stone, and that was the way he burned it. Important thing here to remember is that it's only burned at 950 degrees Fahrenheit. For these 3,000 years, you would have the limestone being burned in a kiln, fired primarily by wood, and kiln technology did not allow, because of drafts and certain things, for the fire to get much hotter than that. So it didn't get very reactive. Any questions so far on the basic line cycle? So now we get into another animal, another beast, and that's natural hydraulic lime. Now I said that there were three basic limestone types, which was the high calcium, dolomitic, and magnesium, but there's actually subcategories. Subcategories would be argillaceous and siliceous. Argillaceous limestones would be if they had little nodules of clay inside the limestone. Or if they're siliceous, they just have pure reactive parts of silica. Now, clay has silica in it, but it has other constituents in it that make it somewhat impure. And what this does is that when the limestone is burned, when you have a siliceous limestone and you burn it, that silica inside of that limestone ends up becoming reactive. And it gives it these hydraulic properties, which is pretty unique because you don't run into hydraulic limes or what's called natural hydraulic limes very often. There's been evidence that it's been used in Roman times, coincidentally, because they're building roads, they're building bridges, they're building aqueducts, and they would go to an area that was locally sourced limestone, and they would burn it and use it and say, hey, this sets up a bit faster. What's going on here? We're going to stick with this deposit. In other cases, they wouldn't slake at all. And that naturally, by adding water, you would actually have to grind it down, and that was counterintuitive for masons and a lot of extra work for somebody to take a millstone and grind down these rocks if they didn't have to. So they thought it wasn't anything good. So you don't run into it too often up until about 1750 or so. But it still has a hexagonal plate crystal structure, and again, it can accommodate these movements. Movements in buildings, whether if a foundation settles or if a wall were to expand and contract an entire length of a street. In fact, I can look right now behind me, or behind all of you, I could see that very long stretches of brick were laid, multiple, maybe 40, 50, 60 feet in some areas. Today, we have to accommodate that movement with things called control joints, like the control joints that you see in a sidewalk every 4 feet, because cements can't accommodate these movements. But lime can, it can flex. And that crystal structure allows that to occur. It also sets bicarbonation, and that, again, that hydraulic reaction with silica. The primary mineral that's formed is B-lite, or dicalcium silicate. These dicalcium silicates are basic minerals that are formed in modern cements, but this sets much slower. So if you were to use a natural hydraulic lime, it won't reach it'll have greater early strength, but it's not going to be like cement where you can walk on it the next day. It would be multiple weeks. Then you get into something a little bit more unique. It's called pozzolanic hydraulic lime. And that's where like before we talked about that you were adding this silica, that reactive silica, inside that limestone to begin with. But afterwards, what the Romans had figured out is that after burning, they could add all different types of things, whether it be brick, tile, fly ash, blast furnace, slag, all these things that are byproducts from different industries that have silica bound into them. But they have to be a right fineness to make them more reactive, to have things set underwater. Again, they also have a hexagonal plate structure. They can accommodate movement to some degree, but there's a bunch of other minerals that can be formed along with the B-light that's formed in the naturally occurring hydraulic lines. So again, we're going to jump back a little bit and talk about the different techniques. So limestone was burned in not just kilns, but something called ricks. And ricks were essentially just a pile formed in a certain way of wood and limestone. And once the pile was burned and tended to for a number of days, it was gone. It's very hard to find any evidence of that, but where we know that we've seen lime materials being used, even if you think about it, the United States, they had to use some type of lime to build a kiln and hold it together. Well, where did they get it? They could have made it here by using a method of using ricks. And if you go to Colonial Williamsburg, you can see them burning oyster shells in that method. Because oyster shells are also a source of this calcium carbonate. Anything, even bones, anything can really work. It would be in the Roman times, it was transported by hand in baskets or carts, and it was all manually done, maybe some animal power being used, and it was also used in that hot lime mixing technology where I said they have the quick lime that's thirsty for water and wants to turn back into a limestone, and they would mix it with sand on site. The difference is that they would actually they'd make it very, very stiff. It wouldn't be any modern mason would use to lay a brick. They'd also use it for plaster, lime washes to freshen up an area for cleaning, because lime is actually, it'll reduce the amount of mildew, and it's antibacterial. Over in Europe, I came across a recent document, what would be equivalent to their CDC, Center for Disease Control, and they recommend whitewashing your barns to protect from H1N1. So it's because of its alkalinity, its pH level, which is somewhere around, once it's cured, around 8 can go up. But when it's fresh, it's somewhere around 11. So it's very costly. Again, there are stories where people would be thrown into the lime pit. There's lots of creative ways to punish people in ancient times, whether it be through some type of boiling oil, but also the lime was right there, and these pits were available. But they would actually sometimes let these pits sit there, these pits of slicing lime, because the longer you let it sit, the better it becomes, the more workable it becomes, the more it can break down and hydrate, and they would use it for fine fresco works. So the very ornate plasterworks you might see in Europe, and to some degrees that you would see in highly ornate buildings in the United States, that's what they were using. Sometimes it would be aged with gypsum, but very small amounts. And the reason for that is because the reason why gypsum is not used exteriorly is because it doesn't hold up. That's why if you put drywall outside, it's not going to work. It's not going to hold up to anything. It reacts with water. So back in these Roman times, around the fall of Rome, there's this concept of Vitruvius, who was an architect who wrote down many different mortar recipes and fundamentals to Roman construction, and we get this concept of a 1 to 3 mix. And you'll see that even today if you look at National Park Service preservation briefs, they always keep it at a ratio of 1 part binder of some sort to 3 parts sand. Well, it doesn't really work because back then they were using quicklime. Quicklime is that burnt stone that doubles in volume when you add water to it. So when these mortars are analyzed, you actually get something that's closer or truer to what would be 1 part lime by volume to maybe 1.5 to 2 parts sand. And not to say that that doesn't work, that 1 part lime to 3 parts sand, but it's very rare because it's also based off of a theoretical void ratio of sand, which I'm going to get into in the next presentation. Like I said, it was quicklime, not hydrated lime. There is a difference. Even though chemically they are the same, one you can touch with your hand and add to water. The hydrated lime, it's not going to do anything. It's just going to turn into this milky putty type thing, kind of like cream cheese if you add the right amount. Quicklime is going to be very volatile, and if it gets in your eyes, it can blind you, it can burn you. Very costly. But they started getting into these pozzolanic mixed designs. And they found that if they took ash from a volcano that they thought was just originally to be sand, that the mortars would set up quicker and they could use it for marine works. Oh, that got them thinking, oh, well, we can build faster, we can build things stronger and more durable. Let's try to stick with these mixes as well. They would also use with, they weren't near this area, it was actually, the word pozzolan comes from pozzolana, which is an Italian word for, if I have it, pozzola. It's some volcano near Pompeii. I can't remember the exact etymology of the word, but it comes exactly from there. You can rework from that. But they would use vitrified clay, the tiles, because again, whether you're using some type of ash or volcanic ash or tile, that main component, that silica, is what makes that lime hydraulic. And I should mention that these pozzolans, if you add water to them, they're not going to do anything. They're not going to do a darn thing. They only chemically react with lime and to some degree cement. And and they've also found that they've used natural hydraulic limes in Britain and France. They've found natural deposits there that we actually still use today around the world. But for a long time, after the fall of the Roman Empire, this Roman cement, the cements that built the Parthenon, that are still standing today, what were the recipes? There's still a debate and chemical analysis of how did they do it. One theory is that when you add pozzolans to things, to lime mortars, it increases the amount of water. And any mason will tell you if you add too much water to a mix, it's going to get weaker. So they would actually use very low water, so it was a very stiff, almost like hard, clumpy clay dirt mix, almost like a soil. Not anything what you would see coming out of a cement truck today, and they hand compact it in layers. So there was this human-powered advantage that you would get that we don't have today, because labor today is expensive, materials are relatively cheap. That's not always the case throughout history. And then they would always use basic lime mortars that were sourced locally. So then we start getting into the 1700s. Yeah. Vitrified. Vitrified. Oh, that word. Okay, that would be where a material is heated up to a certain temperature. So with your firing clay, or if it's something from ash from a volcano, it reaches a glassy form. And it's a good thing you mentioned that, because these silicas need to be amorphous or reactive. And it only happens once these materials reach a certain temperature. Roughly, some type of melt phase could be anywhere from 18 to 1800 degrees Fahrenheit and above. You start seeing this chemistry starting to come about. Is that it? Or
sort of iron oxide.
Iron oxide, specifically?
Is it a glazing? Is it
a glazing? You're talking about like the glazings that might have been in the tile work.
Like in English, in tile. The English brick were vitrified too. I wondered how they did it.
I'm sure on smaller kiln types, you were able to get the fire hotter to be able to get to those temperatures. And I do know that there's certain types of glazing techniques that were used by the Egyptians that are kind of hard to explain, certain blue glazes. That material science I don't necessarily focus on, but I would certainly love to look into it more. And I could talk to you about it more afterwards or in the end of the question and answer. I'm sorry I don't have that information off the top of my head. We start getting into the 1700s, the 1870s, this time frame. This is where things really start to come about as far as these new modern materials that we run into today. So in 1759, John Smeaton, he was in England, he builds Eddystone Lighthouse with a natural hydraulic lime, because he started playing around with these different materials that he was sourcing locally, and he actually added pozzolans to it as well. The documentation on that's a little bit hazy as far as exactly which ones, but there's one called Trax that is sourced from Germany, and that may have been it. So these things were holding up well. They're holding up in marine works. They're setting underwater. This is great for the Industrial Revolution, or the beginning of all this really starting to occur. Right then you have different fireplace designs being brought about. People are starting to think more mother of invention, or drive society forward. So again, another person in England comes about named James Parker, and he was the first one to patent what would be an artificial hydraulic line. So he, unlike the Romans, would add chalk, or he would add clays in the burning process of lime, and then he was the first one to get patent for this. And he called it Roman cement, which it was called a bunch of different things, and depending on what documentation you look at, it's kind of sketchy of where exactly it was used, because Roman cement 30 years later actually means something else. So primary source documents can be kind of difficult. Really the only way to tell is through certain chemical analysis and what can be inferred through reading. But then in 1818 we run into that natural cement. And natural cement is a limestone that has lots of clay impurities. That's that argillaceous type of limestone I had mentioned earlier. And when you burn it, it doesn't look like anything. And in 1818, when the Erie canals were being built, engineers had heard about natural cement from Europe, and they wanted to produce it here. But what they had to look for was cement or limestone that, when burned, did not slake. Nothing happened. And they found that if they ground it down to a fine enough powder with millstones, that it would get hard as a rock within ranging anywhere from 20 minutes to maybe 2 hours. But it was a very durable, still relatively breathable material, like limes. It's kind of what would be, it's this in-between hybrid, and it sets only what it be like. So it has only the reactive hydraulic phases that are slow setting, but it has a lot of it. In 1824, back over in England, you run into Joseph Aspen, who is claimed to be, or regarded to be, the first person to invent Portland cement. And he had added chalks and clays in the burning process. He was able to get these fires hotter and burn what would be this artificial cement rock, and then grind it down. Recent research kind of says that it was actually his son a couple years later, but Joseph Aspen is considered to be the first person to at least moving towards this process of Portland cement. And he named it such because it resembled the Portland stone over in England that they would use as a building stone for architectural purposes. And it was the first one to contain what's called alite, or tricalcium silicate. There's also other things in there called tricalcium aluminates, which cause modern cement, or modern Portland cement, to degrade, and it doesn't. That's why it's kind of problematic today with our built environment. We see bridges and things only lasting 20, 30, 50 years sometimes. That's because the cement, as we're increasing with these strengths, we're getting harder and more brittle. We're not flexing at all. The first shipment of Portland cement was in 1868. So from 1818 to 1868, the United States was using lime and natural cements, primarily for what would be engineering works in, whether it be for canals or military infrastructure, but not on small scale residential building, low-rise residential buildings. If there wasn't necessarily an engineer involved, then it probably wasn't used. But it's always a possibility, a slim possibility, because if the railroad went by, it probably had natural cement in it. And the main quarry, I should mention, was in, even though it was found in Madison County, New York, there were 3 main places that this rock occurred originally, and that was in Rosendale, New York, and within about 100 miles of there. It's in the southeastern quadrant of New York State. The Lehigh District being near Allentown, Pennsylvania, which was actually in Copley, PA, and also there was some areas down in Maryland. Those were the first deposits that were found Because wherever the canals were going, they were hunting these local lime burners and trying to find out which rocks weren't slaking as the progress moved forward. So for all these years, it took the United States a really long time. I mean, almost 50 years to get a hold and to get a grasp of this Portland cement because of industry and people investing in this concept, because we're trying to advance and move forward as well with the rest of the world. So in the 1870s, that's where things start getting even more and more out of control. In the 1880s, you end up getting experimentation with the rotary kiln. So with all these kiln types that I had explained to you before, they were shafts. They would be on the side of a hill. They would be basically tall, and they would layer limestone, coal or wood, limestone, coal or wood, and alternate between the two. And it was very inefficient, and they couldn't necessarily control the burning temperature. But with Portland cement, you have to control these temperatures, otherwise you get an inconsistent product. When people are engineering structures, they want consistency. So that, again, mother invention, you end up getting something, the rotary kiln. For a long time, these imported Portland cements from Europe were fighting to be the main competitor on the market because they were trusted, they were predictable. And only up until 1896 was the first time that the United States actually exceeded this production. But it still didn't really exceed natural cement. It took a couple years for that to occur. So we have a bunch of different mortars, different things being used, again, primarily in these engineered systems. 1904, 1950 rotary kiln becomes perfected in its design. And now Portland cement could start running and building all these superstructures, early skyscrapers, because it's set up harder and faster than any other material. And in a mortar, as a cushion between these masonry units, between these bricks and stones. Because, like I said, the lime takes a while to get hard. It stays flexible. Cement can take only a few days, or 28 days would be a standard for building construction. But you might not necessarily be able to lay another story of brick like you could because it's slower setting, compressive strength isn't quite there. And that's because it's burned at 2,400 degrees. That means it reaches a melt phase. It becomes what's called clinker of cement, and it's glass. It becomes this glassy, just like these pozzolans that we were talking about earlier. They have to get to these very high temperatures. Even in 1914, there were people I took this article from Engineering News, and why not preserve the natural cement industry? So people saw the merits of still using this product that's been around for almost 100 years. It's been worked fine for engineering projects, but Portland cement wants to keep growing. I should mention that natural cement's burned at a lower temperature. It's not necessarily burned at 2,400 degrees versus that 950, maybe around 1,100 or so. So there's less embodied energy. At this point in time, people really didn't necessarily care about energy efficiency or the amount of pollution that's going up in the air. They just want to be able to move forward with their projects and build higher today than tomorrow. I mean, if you think about the Empire State Building, that was being constructed in, what was it, about a floor a day pouring concrete. That's insane. You could never do that with lime. Not even what would be pozzolanic hydraulic lime. It just wouldn't work. So as we started moving forward, Portland cement, like I said, reigns in engineering projects. Inside, that's a photograph of the Hoover Dam. And even there's so much cement that was being poured in a day. Cement actually releases energy. It heats up quite a bit. And in order to slow it down, they would add pozzolans to it. They would add pozzolans because the pozzolans would consume some of the heat and make it set up sooner. Make it take away some of the hydration. The heat of hydration would be slowed. From what I've heard, they had to run water conduits through this massive dam just to keep the whole thing from exploding or getting too hot. It had to be cooled down in some way or another. We get something else called slag cement. slag cements are blast furnace slag, left over from steel manufacturing. Those would be ground down, used as a pozzolan, mixed with lime, voila. Yeah, the weird thing is that once you hit World War II, all these things start fading away. And only domestically produced, you might find people, old traditional masons tend to be set in their ways. I know they are today. If they've been doing something for 20 years, they tend to stick with what they've been doing, unless they want to try experimenting and they're inquisitive. So they might have stuck with the lime putty mortars, or maybe their natural cements if they could get them, and use them in their building construction. But again, only local buildings, smaller projects, out in rural communities. And then you get something called 116, and that becomes the mix for building all masonry in North America. 116 stands for 1 part lime by volume, 1 part cement, and 6 parts sand. So if cement's so great, why would they add lime? Because cement is a very dead material. It doesn't work. It's burnt to a crisp. It's turned into a glass. It doesn't have flow. It's not very friendly to use. The practical applications are limited when laying a brick. It mason would be screwed. Yeah.
Well, you're getting more tensile strength in Portland, and it cures in about 30 days. And hydraulic lime cures in how long? And does it ever attain that compression strength?
It can. It depends on ideal curing conditions, and I would argue that even this mix of lime, cement, and sand doesn't always end up reaching its desired strengths either.
And when you say lime, and you're talking about Portland mix, then you're also talking about something that was kilned at a higher temperature than the 900 or so that you were talking, or are you talking about the regular hydraulic lime?
I'm talking about just regular hydrated lime. When I'm referring to lime, only hydrated lime. That is.
And that's what we buy today.
That's exactly what you buy today, and what's been, to some degree, for simplicity, what's been used for 3,000 years for the most part.
ASTM C207.
Yes. But it's not manufactured the same way because it's manufactured at a higher temperature. Am I right?
To some degree, yes. I've tried to find out and beat down on people's doors to find out exactly if it is, and in some cases, it's not. If you're using a high calcium lime that you can get sourced from, there's a couple companies. One I know is called Mississippi Lime. They sell lime putties that aren't burned at necessarily the higher temperatures. But what's commonly available, which is known as Type S hydrated lime, that's used in this 116 mix that's still emitted, that is, from what I've seen, burned at a higher temperature, just high enough to get enough out the door, but that it's not detrimental for a Portland cement blend. So if you were to take away that lime from this mix, you get something that doesn't work. Okay? If you take away the cement and use the lime that you can get today, it doesn't really work. So yeah, thank you for pointing that out. Keeping things on point. And again, you start getting into this concept of restoration, beginning with high lime content mortars. That's where you would end up using maybe 2 parts lime and 1 part cement and 9 parts sand. And that starts in the 1960s because they couldn't get the limes that had been used historically. And a lot of information was lost. And in my opinion, the Portland Cement Association would pump a lot of mumbo-jumbo out into the world, and we have the internet today, so it's very easy to find a book on Google Books from 1870 than it was maybe for researching at your local library. They didn't have it, you might not know what you're looking for. And I don't know how many people were necessarily researching this because they would commit to using high lime content mortars with some cement and just a little bit, which has proven to be detrimental in mixes today. Because that little bit of cement, remember I mentioned that A-light phase, that tricalcium aluminate that Portland cement offers, those actually will accelerate deterioration of that lime, whether it be a good or bad lime. Good or bad being either what is produced today being bad, more or less bad at these higher temperatures that doesn't work on its own, or if you're using a high calcium lime that's very pure and more reactive and can be burned at a lower temperature. And then, of course, well, not of course, but in the mid-1990s, excuse me, this lime renaissance begins. Because of all this history that's mentioned here, I've mentioned some things about Europe and in England, but really lime never went away. Hydraulic limes never went away in Europe. Pure lime mortars never went away in Europe. They saw the merits of not using cement. That in certain parts of, I believe in Norway, you cannot even use any type of lime mortar that's not slaked for at least 18 years on the restoration of a church, because the buildings are that old, and that's exactly what they used so many years ago. So the standards are much higher. And we've been starting to implement these things beginning in the 1990s, moving away from the lime, this 116 mix, which was specified, or 129. Again, the first number 1 being cement, second one being lime, the last digit 6 or 9 being sand content, which also, I should mention, follows that mysterious binder ratio, 1 part binder, lime and cement combined or by itself, to 3 parts sand, which also doesn't really work very well, unless you have that extra cement to give it extra strength, and nobody really knows the difference at the end. It's hard and usually good enough. Let's see what we have here. Okay, so if we can compare all these different things that I talked about, just to kind of sum it up, the more hydraulic a mortar, the greater its strength. And that's because of the more B-light or A-light or whatever it may be. The lime mortars are the slowest setting. That's because they use carbonation and B-light, which is the slowest setting chemical composition that's occurring. Portland cement is the fastest setting that has A-light. That's what gives the very high early strength in a mortar. And then pozzolan consumes the free lime, which is something I want to touch on. Free lime is, when I talked about these plates in the lime that allow it to flex and move, if a fissure or a crack were to open up, this free lime, it's something that maybe has not fully reacted, and it's in the mix as it's setting, and it's still workable. What's evidence of that is in old castles, if you dig deep enough in these 10-foot thick walls, you actually find lime putty still in some areas that has yet to ever carbonate, because carbon dioxide could never get to the inner core of these walls, which are so dense. And the pozzolans, they consume this free lime, and they end up gaining strength that way, causing a hydraulic reaction. Just like in the Hoover Dam, where how did it get harder and gain strength? By consuming the free lime in Portland cement. So with flexural strength, more free lime, the greater the mortar's flexibility. High calcium limes, natural hydraulic limes, have the most free lime, thus the greatest flexibility when compared to whether it be a slag cement, which is basically pozzolans and cement mixed together. And also it reduces the amount of self-healing ability, because that free lime is being consumed. Here is just a basic data chart. Something I really think is important is, as you get stronger and denser, the less vapor can transmit through a building. So we talked about what is a mortar. It's that stuff in between the brick. Yes, bricks are irregular, stones are irregular. You need to put something in between. But it's also the sacrificial part of a masonry wall. It's much easier to replace mortar than it is a brick. It's much easier to replace mortar than it is a stone, especially if it has some type of significance, if it's in cars. A lot of time was put in its manufacture. So when there's moisture in a wall, it needs to go somewhere. It's supposed to go through a mortar joint, not necessarily through the brick, which I'm sure if you walk around any town, any city, you can see where cement has been gone over top of a mortar joint that was lime, and the bricks falls apart, deteriorates, and traps it. So here this was from a recent study published in the Association for Preservation's Trades Journal. The first 2 bars indicate the breathability or vapor permeability of Portland cements. Those are the first 2. Then we have the high calcium limes, And the dolomitic limes, wind mixed with sand. Then we have the type N over here. And then these are those 129s, also known as type O mixes. And the natural hydraulic limes. And I was actually very surprised to see how close they fall in between the pure lime mortars and also the how close they are relative to one another. They are actually much more permeable than the study that I have seen. But this was released probably like in the past 6 months or so. And questions are answered. I'm sure I'm running a bit late.
Type N, type F. Does hydraulic lime also have similar capabilities, or is it?
No, it will allow, it will keep out water from penetrating, but it will still allow moisture to pass through. So it won't allow water droplets to necessarily pass through, but any kind of water vapor can still be transmitted to and from. Modern, which I'm going to get into the next component, is how these mortars and this chemistry is applied.
So, say you're applying stucco to the rainy side of a building, like a stone farmhouse. In that situation, would we be better off to use something that's less porous and more likely to resist the moisture?
Well, in that case, I would recommend using something that would be more flexible to accommodate the movement of an old farmhouse, because that wall, if it's built with what would be a rather flexible and vapor permeable mortar to begin with, you don't want to trap that water. A misconception would be not so much water getting into the building, but water being able to escape outward from the inner core. Because as we're all here in this room, we're releasing moisture out from our bodies. And these walls, to some degree, would breathe if they were uncoated with anything, as long as there's some type of breathable membrane.
Well, a lot of times, in reality, there's a dirt and a very soft stone in the 18-inch wall in the core of it. And then there's plaster on the interior side of it, and there's obviously a wind-driven rain coming up against that gable or that wall, and water transfers through, and then it causes the plaster to decay, and as a result of that, you have to come up with a solution that's going to work. And in the past, we've used a Type S mortar, which basically retards the moisture from getting anywhere inside of the stone. It goes to the way those stone walls were laid initially too, because they were using a lot of dirt and mud and the binders often were things like animal hair, and sometimes you'd see oyster shells, but it looked more like the color of dirt. And I guess what I'm asking is, if you put the hydraulic lime up there and it's more porous, is it going to resist the wind-driven water from coming in?
That it will, because just like that can be seen, if it can be used in, right off the bat would be, if it can be used in marine environments and it holds up in a durable fashion for many, many years in the ocean, I don't see why it wouldn't work on a stone farmhouse. My only reason why I wouldn't say, why not use a Portland cement base, is because if you're covering, those walls can be pretty long, pretty big, square footage wise, and there I'd be worried about cracking. And if a crack were to open up, that gives a place for water to find its way in directly.
I agree, but a lot of times if water's in there, that crack will present itself because water is in the wall. So I spent my whole life trying to keep the water out of the wall.
But if you keeping water specifically out of the wall that's a fight that's probably too difficult to try to be able to work with it to allow it to slowly escape on its own through wetting and drying cycles. If you had cement versus a pure lime or a hydraulic lime on a building, it's not going to be able to get back out and pass through that Portland cement-based stucco or plaster application. It'll try, and it might get to the surface behind it, and then it would freeze and crack. If there's water vapor transmission to allow it to pass through, such as in a natural hydraulic lime or pure lime, it can pass through. another thing I should mention is the porosity. Pores of limes in general can accommodate freeze-thaw resistance. They have a greater freeze-thaw resistance. That's why we would add, or developed in the 1940s, we would add things called air entrainers, which would create little pockets and bubbles to resist water vapor inside cement from crystallizing and freezing. So it gives a place for that water to expand. Limes tend to do that better because of it. It has an open pore structure. Cement tends to have a very closed pore structure. They're not interconnected. So it's porous, but the amount of pores that interlock them are not nearly as great. I hope that answers the question or attempts.
Yeah.
Were there any other questions? Yeah.
What about a product like Anti-Hydro?
Anti-hydro.
Anti-Hydro from over in New Jersey, you know, that is an additive that gets put into waters for waterproofing purposes. What does that do, or what's good or bad about it?
I've seen from most waterproofing products that I've seen, if they're not, sometimes if they're additives, they will help. Like specifically on a foundation wall, I would say yes. If you're going to parge a stone wall that's below grade and there's water infiltration because of hydrostatic pressure, then yes, putting an impermeable membrane on the exterior, that's a great idea. If you could tar it, that would even be better. But for most buildings above grade, it's really unnecessary. I mean, there are plenty of buildings that you can look at. I've been standing for 200-300 years that didn't have waterproofing products on them, and they're holding up fairly well without causing any accelerated deterioration. The worst cases that I've seen is that if the waterproofing product's been put on the exterior of a building, there's lots of different things that can go on from a case-to-case basis, is what you had mentioned earlier, the interior plaster can then come off because that moisture that's already in the wall will try to escape, and it's going to go either out or in, whichever is easiest for the water to go for wetting and drying cycles. So I wouldn't use it unless, again, it's below grade or in very special circumstances.
But the Anti-Hydro is used as an additive to the mortar that you build the wall with, as opposed to a waterproofing on the exterior of the wall, or at least it can be.
Right.
It does something to the cement to densify or waterproof it, or I don't know what it does exactly.
In modern construction, which is what I'm going to be touching on in just a minute, there's different theories behind wall construction. So there, if it's one mass component, you have an isolated place where, you know, if you're building a wall with anti-hydro, I'm sure you're going to be putting in control joints at the appropriate stages to accommodate any type of movement, and if the walls were to crack, it's going to crack at like a caulk joint of some sort. So,
I worked for a major brick manufacturer for 2.5 decades. Any of us are going to, who are involved, are going to tell you don't use water repellent additives in water when you're laying bricks. Just don't do it. If you have a problem, don't come and complain to the brick manufacturer. Don't do it. If you're using concrete masonry units that have integral water repellents, you must use integral water repellents in the mortar. If you use integral water repellent in the mortar and don't put it in the concrete block, you just wasted your money. Okay. Don't use it with clay brick.
thank you. Are there any other questions?